Hi, everyone. Thanks so much for having me for this Rylum Rock and Talk. We're going to be covering alkali silica reaction, a little bit about research needs, and a link to practice today. I'm Jason Eideker, and I'm a professor at Oregon State University. So a little bit about me. My research group does fundamental cement-based materials research. We focus a lot of our efforts on alkali silica reaction, looking at test methods as well as preventive options. I also work on early age properties of calcium aluminate cement-based materials. And a lot of my work is related to translating our laboratory experience into what's happening in the field and into standardization efforts. I've been working on ASR since 2001 when I was an undergraduate at Georgia Tech. I was also co-author of the ACI 201.2R-16, which is their guide to durable concrete. And along with Mike Thomas, we really rewrote the chapter on alkali aggregate reactivity. I'm also currently secretary of ASTM C1260 risk management for alkali aggregate reactivity. And just recently, I started as chair of a Rylum technical committee. It's called TCASR, very fitting now. And we're going to talk about that a little bit later on today. But that committee is really working on risk assessment of concrete mixture designs that incorporate alkali silica reactive aggregates. So as I mentioned, alkali silica reaction actually falls under a subclass of a larger reaction called alkali aggregate reactivity. And ASR is responsible for at least 99% of all cases, if not even more. There's a second type of reaction, though, called alkali carbonate reaction, which is responsible for less than 1% of all cases of alkali aggregate reactivity in concrete. We're not going to talk too much about ACR today, but just so that you know, it's a reaction that occurs between alkali hydroxides and certain argillaceous dolomitic limestones. And that reaction is characterized by a very rapid expansion and extensive cracking of the affected concrete. ACR is quite serious because of how rapid and damaging the expansion is, but fortunately it's quite a rare variety of AAR, and we generally know which aggregate sources those are linked to. Alkali silica reaction, on the other hand, is associated with the dissolution of silica in and from the aggregate and the subsequent formation of an alkali silica gel, or maybe a better term is an alkali silica reaction product that forms within the aggregate, and eventually as it cracks the concrete apart, that alkali reaction product will continue to work its way throughout the entire concrete matrix. So just a brief note on alkali carbonate reactivity and prevention. Well, there's a bit of a debate going on right now in our research area. Is this really just a form of aggressive ASR? I don't think it's been decided yet, but you can read some papers in the literature on it. But one of the main takeaways is that if you have an aggregate that is alkali carbonate reactive, none of our traditional preventive measures that we use for ASR actually work for ACR. So our recommendation is to avoid that for use in concrete construction. That aggregate might be great to use in asphalt or for base material, for riprap, for sort of embankment stabilization, but should not be used in normal concrete. So a little bit about ASR. So this was first discovered in the late 1930s by Thomas Stanton, who worked at the California State Division of Highways. We now call that Caltrans, or the California Transportation Department. And this was discovered in Monterey County and in Los Angeles County. And you can see a nice image of Thomas Stanton there standing next to a concrete column affected by ASR. So for ASR to occur, you need four things. You need a source of calcium, you need sufficient alkali, you need sufficient moisture, and you need reactive silica. So calcium generally comes from the cement or the supplementary cementitious materials. The reactive silica we're talking about in this case comes from the aggregates. It could be either the fine aggregate or the coarse aggregate or both. You also need alkalis to be present. Again, this mainly comes from the cement, but also can be contributed by supplementary cementitious materials. It can be contributed by aggregates, external sources such as de-icing chemicals, and chemical admixtures as well. And then you need sufficient moisture. So, hopefully we're all aware that there's pore solution inside concrete, and concrete that's exposed to a moist environment, something with a relative humidity greater than or equal to 60%, could be subject to ASR. So we generally don't think about ASR occurring in the interior of buildings, concrete inside a building, unless you maybe have a leak, something like a plumbing leak or a swimming pool, for instance. But generally, we're talking about concrete that's exposed to the environment. So dams, bridge decks, pavements, columns, those types of things that would be in exterior concrete. When we're talking about reactive silica, it's important to sort of note what we mean is that we mean silica that has gone through some sort of straining. You can see an image of quartz there on the left-hand side with a very regular crystalline pattern, very strong bonds between the silica and the oxygen in that case. On the right-hand side, though, you see something like opal. So this is our most highly amorphous form of silica. And those bonds are weak, they're strained, and they're more easily attacked in the high pH of the concrete pore solution. And so if you have this sort of perfect storm of having reactive silica present, you have moisture, you've got alkalis, you've got this high pH inside the concrete, and you've got calcium present, you can get ASR that occurs. And this is some of the outward manifestations of what this looks like. You can see a pavement in the upper left-hand side that's cracked from ASR, part of a foundation in the lower left-hand side, a foundation for an electrical transmission station. And then on the right-hand side, part of a concrete footing that was supporting a bridge in Quebec City, Canada. So one of the things that we talk a lot about with ASR is evaluating aggregate reactivity and then evaluating prevention efficacy. We do a lot with accelerated lab tests. We're generally talking about small-sized mortar or concrete that are stored in some sort of an accelerated condition. We're going to talk about test methods a lot today, so I thought I'd introduce some of the main ones that I'm going to be talking about. You'll hear me talk about the accelerated mortar bar test, or AMBT. In North America, we typically use the ASTM standard, ASTM C1260 or 1567. And this involves casting 25 by 25 by 285 millimeter bars. So these are mortar bars. And those are subjected to 1 normal sodium hydroxide. They're submerged in that. And they sit in that at 80 degrees Celsius for a period of 14 days. And we monitor the length change of those bars over that 14-day period. In a concrete prism test, we go to a slightly larger cross section, so now 75 by 75 millimeters, but the same length. This is run at 38 degrees Celsius for a period of 1 year if we're just assessing aggregate reactivity, 2 years if we are assessing any prevention methods. And then we also use outdoor exposure blocks, mainly to benchmark against our accelerated laboratory test methods. So, of course, as we move from these smaller size prisms all the way to outdoor exposure blocks, and certainly even at looking at a field structure, you get increasing reliability, but you also get an increasing test duration. A test we've been using lately is fairly new. It's called the miniature concrete prism test. In the US, this is standard AASHTO T380. And this involves casting a 50 by 50 millimeter cross section. So we're sort of between the accelerated mortar bar test and the concrete prism test, but we can actually use a full-size concrete mixture design and normal sized aggregates in this mixture, which is one of the advantages. This is run at 60 degrees Celsius, but those prisms are still submerged in 1 normal sodium hydroxide. Currently, the standards for expansion in this test are to assess the expansion at 56 days, and a mixture that would be said to pass the test or to have an effective prevention measure would be less than 0.02%. Something that's uncertain would fall between 0.02 and 0.025%, and something that was not effective would be greater than 0.025%. One of the things that this test needs, though, because it is so new, is benchmarking against our outdoor exposure blocks as well as real field structures. There are also a number of RILEM test methods, and I'm not going to cover all of them here, but AAR not or AAR 0 is the outline guide to using RILEM methods for assessing alkali reactivity potential of aggregates. And it will sort of step you through what the different test methods are and what advantages and disadvantages they have. AAR2 is the accelerated mortar bar test, essentially, that I just covered. AAR3 is the concrete prism test. Those are just the companion test methods in RILEM. A fairly new method that has just come out is AAR8, which deals with the determination of releasable alkalis from aggregates in concrete, and AAR13, which has also just recently come out, which is applying alkali wrapping for the concrete prism test. So essentially a modification to AAR3 by wrapping the prisms in an alkali saturated cloth type material to help prevent leaching in that test. So some new test methods that you may want to look into. There are also quite a few other test methods from RILEM, but I will let you explore those on your own. So we're going to be looking at results from expansion tests, and I just wanted to give you an idea that typically what you're looking at is some sort of an age along the x-axis. In this case, this is showing months for the concrete prism test, and then expansion along the y-axis. And you can see that for this particular test method, a non-reactive aggregate would fall below 0.04%. Something that is moderately reactive in this case would be around 0.10%, and a highly reactive aggregate would be around 0.22%. So the takeaway from this is that not all aggregates expand the same amount. They can have different reactivity levels. In the case of the non-reactive line, perhaps it could be an aggregate. It may also be a combination of a reactive aggregate with a prevention option that we would be trying to assess in this particular test method. So we know that we can prevent ASR in new concrete. Most supplementary cementing materials can be used to control ASR, and this is our most popular prevention method, but it depends on the composition of the SEM. Pay particular attention to the alumina. We're going to talk about that a good bit today. It also depends on the dosage rate, how much of the SEM you're using, the nature and level of the aggregate reactivity itself, also the alkali content that's supplied by the Portland cement and other sources that I mentioned before as well. So how do SEMs actually prevent ASR? So one of the main things that they do is that we produce more CSH and or more CASH once we have SEMs present. We know that those can absorb more alkalis from the system, and having a lower calcium to silica ratio is better. We also know that ternary blends tend to be the most effective at preventing the alkali silica reaction. We also get better mechanical properties, so we might have a bit more resistance to those expansive forces coming along from ASR, and we refine the pore network, right? So we make it more difficult for aggressive agents or for water to come in. One thing that you'll note about the presentation today is that I've peppered in a lot of different references. Some of these are classic, sort of seminal references. Some are quite new. There are thousands of references out there for ASR. So I'm trying to give you just a starting point to go and look at some literature. One of the other things that SEMs do, especially those that are high in alumina, is that they can contribute alumina to the pore solution. And we know that that helps to protect the silica from the aggregate from dissolving. And of course, we use less OPC, so there can be a dilution there and a reduction in the alkalis coming from the Portland cement. But we have some questions that remain. What about SEMs with alkalis? And how long do alkalis actually remain in the CSH or CASH? What about aggregates that can contribute alkalis as well? So we're going to talk a little bit about this today, but these are also some questions that you may want to explore in your own research. So some recent research that was done by Theo Chape and Karin Scribner really showed the importance of having alumina in the pore solution. And if you look at this figure shows the reacted fraction of aggregate on the y-axis, and it shows the time along the x-axis. And you can see there are 2 points here highlighted in red. And those show the reacted fraction of aggregate at those particular points. And what you can see is that when you have no alumina present, you can see a lot of damage in the aggregate, a lot of dissolution from that silica. But once you have a sufficient amount of alumina in the pore solution, what you can see is that you really protect the aggregate. So having that alumina present is really helping to prevent dissolution from silica in the aggregates. We've also been doing some work recently on looking at how Portland limestone cements affect prevention methods. This was work done in that miniature concrete prism test. And what you can see is there's basically sets of 3 groupings of bars. The first bar in each grouping is a parent Portland cement without any limestone in it. The second is a 15% replacement of intra-ground limestone. And the third bar is a 10% replacement of interblended limestone. So really the main takeaway from this is that the mixtures with Portland limestone, the mixtures for Portland limestone cements really perform similar or even better than the parent Portland cement mixtures on their own. One thing that you'll note is that several of these mixes did exceed the expansion limit in the test. And those were with a fly ash that I'm calling fly ash 2. This happened to be a fairly high alkali ash with a 4% sodium oxide equivalency and a very low alumina content, about 16%. So you would need even more of this particular fly ash to get you below the expansion limit in this test. Some work that one of my students did a number of years ago really looked at this importance of having alumina present in the fly ash. In the figure on the right-hand side, you can see that if we were able to have an alumina plus silica amount in our total cementitious materials of greater than 36.5%, we could keep the expansion below 0.10% in the accelerated mortar bar test. We also did some work to take fly ashes that had lower alumina contents, and we artificially augmented that alumina content with just a powdered alumina trioxide. And that actually worked incredibly well to increase the efficiency of the fly ashes with lower alumina contents. So how do we go about preventing ASR in fresh concrete in other ways? We know that lithium can be used to control ASR, and it may also be able to be used in combination with supplementary cementitious materials, but it really depends on the aggregate reactivity level. We also know that restricting the alkali contribution is key. So it's not just the alkali content of the Portland cement, but the total amount of alkalis present in terms of how much you have in kilograms per cubic meter in a concrete mixture. Also, avoiding reactive aggregates could be possible, but this is usually not an option. It's only something you might consider in a highly critical structure. So modeling isn't really my expertise area, but I do think that is something that is really important. And so I've given you just a couple of references that you can go to here. We did a review paper in 2015. One of my co-authors on that was Cyril Dunant, who's done some excellent modeling. You can see one of his papers highlighted there from 2010. Also work by Multan and co-workers looking at modeling as well. So again, this isn't my expertise area, but if modeling is something that you're really interested in, here's a couple of good references that you can use as starting points. And I think this is something that we need to be really doing more and more of in the area of ASR. So why are proper test methods so important? So I'm going to show you a little bit about a particular case study that I've been involved with for about the past 13 years. So this is the Mactaquac generation station. This is a hydroelectric dam. And this is in New Brunswick, Canada. So just on the sort of far eastern and bit northern part of North America. And when this dam was constructed in the 1960s, they knew of ASR. It was just really beginning to be a concrete durability problem that was gaining attention. The test method at the time was called ASTM C1260. These were mortar prisms that were stored over water at 38 degrees Celsius. And the test method at the time showed that the gray wacky aggregate was non-reactive. But this test method had some flaws with it, especially related to excessive leaching in the test. And so unfortunately, after about only 5 to 7 years in service, the dam operators started to notice some strange things happening. They got impingements in the turbines. They were not running as smoothly as they should have. And they started to do some investigations. And what they found was that they had alkali silica reactivity going on in this dam. New Brunswick Power, who is the owner of this dam, spends about $7 million a year just to deal with the ill effects of ASR. They can't stop ASR from occurring in the dam, so they have to do options to try and deal with the expansion. The intake structure has grown vertically by about a foot over its lifespan due to ASR. This dam is restrained on either end by bedrock, and it's cast on bedrock as well. So the only place it can really move is to grow up or to expand inward and crush things like the penstocks that are carrying water from the head pond through the turbines to generate electricity and out to the rest of the river flowing out from the dam. So the way that they accommodate the expansion in this structure is that they take a slicer like you would slice cheese with, and they literally cut through different parts of the dam to relieve the stress that's occurring. Since they started slot cutting, they've removed about 2.5 feet of concrete from the dam. It's estimated that there are about 120 to 150 microstrain of unrestrained expansion, and this has not slowed down at all, at any point in the dam's lifespan so far. Originally, the service life for this dam should have been 150 years, but it's not going to last that long. The big question is, how long will it last, though? And there were a lot of thoughts of looking toward complete replacement in 2030, but I'll tell you that we're not quite sure what's going to happen with the dam now, and I'll get to that in a moment. This is an image of some of the slot cutting that was happening when I visited the dam. I think this was in about 2015. And you can see these nodules along that wire are actually coated with diamond, and they literally will slice through different parts of the dam. They use a finite element model and their monitoring of expansion to determine where the highest stresses are and where they need to do slot cutting every year. So I said that this is slated for reconstruction in 2030, but there is a push right now to see if they can continue to operate this dam out to 100 years. So if you want to read a little bit more about this, I encourage you to look at this link and start to see some of the efforts that they're going to try to keep this dam in operation. Because the expense of constructing a new dam so soon into its intended lifespan is really something that the owner is trying to avoid. So this sort of brings us into, how do we specify concrete that is resistant to ASR? So there's really two main approaches: either a prescriptive approach, where you tell someone use 30% fly ash based on this particular aggregate reactivity level, and you should prevent the reaction from happening, or a performance-based approach, where you tell someone to run a test method, run the concrete prism test or run the accelerated mortar bar test to determine how much of a prevention level you need. In North America, we have a fairly unified approach for this between CSA, ASTM, AASHTO, and Federal Highway. ACI, the Guide to Durable Concrete, gives general recommendations, but not a prescriptive or performance-based approach like those previously mentioned standards do. The standard I'm most familiar with is ASTM C1260 and this is risk minimization for AAR. So this does have both prescriptive and performance alternatives in it, and it allows for the use of reactive aggregates either by limiting the alkali content of the concrete, using fly ash, using slag, or using silica fume. But the actual level of prevention varies with the risk, and that risk is defined by how reactive the aggregate is, what the service life of the structure is, and what its exposure conditions are. So I think right now, probably our biggest practical challenge is the reliability of current laboratory accelerated test methods. We use outdoor exposure sites to benchmark our test methods. And what we're really looking for is to have this type of a relationship between our exposure block expansion, if you were to plot that on the y-axis, versus the accelerated lab test on the x-axis. Either a pass-pass or a fail-fail result is fine. Both methods are telling us the same thing. But what we want to avoid are situations where we would be in a pass-fail type region, where it would pass the accelerated lab test but fail in the field. That's the most concerning region to be in. And if we look at some of our data from outdoor exposure sites, this is from the outdoor exposure site in Ottawa, Canada. The black squares are expansions at 15 years, and the light gray triangles are expansions at 10 years. So at 10 years, things looked generally like we had good agreement in this sort of pass-pass or one block in the fail-fail region. But what you can see is that at 15 years, we started to see those triangles shift. And now the measurements at 15 years shows us that even though we passed in the accelerated version of a test in the lab, the concrete prism test, we're actually getting failure and expansion in the outdoor exposure blocks. This is just a snapshot of some results from the outdoor exposure site at the University of Texas. And basically the takeaway from this is that really none of the preventive options that were predicted to have worked in accelerated tests are actually working in the field. If you note here on the upper right-hand graph, 40% of a particular fly ash seem to give the most prevention efficacy for a particular reactive aggregate. You can see in the lower left-hand side, a ternary blend of 20% fly ash plus 5% silica fume is really giving the best prevention for this particular fine aggregate in this case. But you can start to see that even after 6,000 days, we're starting to see some expansion in those blocks. Now, certainly the amount of expansion is much less than the control for this particular case, but you can see that a lot of the other preventive measures are expanding quite a bit, and this is a real concern. So we've been doing work with the miniature concrete prism test. Again, this is designated as ASTO T380. We also looked at a couple of emerging test methods, the concrete cylinder test and the UNB concrete cylinder test, but I'm not going to cover those here. And we looked at validating this across a wide range of aggregates for reactivity testing, but so far only a minor work has been done with SEMs. So that's what we've really been looking at here. So the takeaway from this slide is that we looked at a bunch of different mixtures at 3 different laboratories, and all of these prevention options were options that were shown to pass the accelerated mortar bar test or pass the concrete prism test, but all of these mixtures expanded more than 0.04%, which is the expansion limit we use for outdoor exposure blocks. So if we look at the miniature concrete prism test results for these mixtures, what the main takeaway from this is that the concrete prism test had 7 false negatives for it. So 7 mixtures passed the concrete prism test, but actually failed in the outdoor exposure blocks. But in the miniature concrete prism test, only 1 mixture was a false negative. So this gave us some indication that this could be a more reliable test method. And we're now doing a much larger project to look at the possibility of using this test method as a replacement for our other accelerated test methods for evaluating prevention options. So just in the interest of time, I'll go through this slide fairly quickly, but one thing you can see is that the exposure block expansions shown here in this sort of mustard yellow color, those are all mixtures that have failed in the field. And you can see that the concrete prism test really didn't pick up many of those mixtures as potential for failing. It passed a lot of those mixtures. You can see the miniature concrete prism test, though, has done a much better job of picking up those prevention methods as those that would fail in the field. So some of the takeaways are that we have some areas that are really well understood. So especially on the prevention mechanism side, we know CSH and CASH with a low calcium to silica ratio generally work the best for preventing ASR, and we know we can get that with supplementary cementitious materials, especially ternary blends. We know having alumina present reduces silica dissolution. We know that having a lower alkali content as well as using lower alkali cements are particularly effective. And as I mentioned before, we know ternary blends tend to be quite effective. But there's a lot of areas where work can still be done. We have this disconnect between accelerated test methods and our field experience. Determining alkali thresholds of aggregates is something that's gaining a lot of interest and importance. Proper mixture proportioning to avoid ASR and being able to take into account aggregate reactivity into that is something that still needs more data behind it. Alkali availability from SEMs continues to be, I think, one of our really big challenges. So if you're looking for something to work on for your PhD, I think that's an area that could really use a good bit of effort. And as I mentioned before, modeling as well. I think we have a strong start, but this is something that we can capitalize even further on. So as a PhD student, how can you get involved? I think one of the best things you can do is to get involved with some of the RILEM technical committees. I'm highlighting one here. This is RILEM TC ASR. I'm the chair of this. Professor Clartia de Wert is the deputy chair. And this is just starting, and you're welcome to join this. We have 3 different work packages. Work package 1 is looking at validating existing test methods, right in line with some of the things we talked about today. Work package 2 is looking at alkali inventory and validating that new RILEM test method I mentioned, AAR8. And all of this is going to feed into work package 3, which is a framework for risk assessment of concrete mixtures with ASR susceptible aggregates. So I really encourage you to check these out. There's a second RILEM TC that also just started. It's called RILEM TC-ARM, and it's dealing with what happens once you have ASR actively going on in a structure. And so what mitigation options can you do? So if you're interested in that side of things, I definitely encourage you to check out that RILEM TC as well. We also have a workshop coming up, the Corvallis workshops. This will be our 4th one. This is going to be hosted in Oregon. So come for a visit, come and see us. This will be June 22nd to 24th of next year. And we're also going to have a doctoral short course associated with this. So if you're interested in that, I've got the 2 web links there that you can check out. So with that, I'll just say thank you. I have a few references here for you. And we'll open it up for the question portion now.